Thank you very much for that, Chris. Yeah, I do like to every once in a while say, I sold out the European Astrofest. I usually try to hide the fact that I was only the opening act for Brian Cox, but I'll still claim that one as being me. This is one of my favorite topics, and it is the topic that probably resonates with, everyone. You don't have to be interested in astronomy and astrophysics to have thought about this question about whether we are alone in the universe. It's not where I started my career, as Chris was saying during the intro. I did start off in instrumentation and then moved into cosmology and the history of the universe. But as time progressed, I started to give a little bit more thought to this question about whether we're alone. I'm not sure how unique and novel my thoughts are on this, but it is something that I am passionate about in the way that everyone is passionate about this question. I don't think I'm going to answer the question whether we're alone or not over the next sort of 45 minutes or so, but hopefully I'll give you a few things that maybe you haven't thought about before. And some of them are maybe things that are not challenging, but things that might at least cause you to take pause about what the answer to this question might be. So I wouldn't say it's a negative talk, but I am going to try to focus on some of the challenges, let's say, that complex biological life might face in terms of taking root and evolving into something more complex with it, however you want to define that. So that's sort of the general background of where I'm heading over the next little while. I'm not the only one who's given thought to this. Like I say, I think all of us sitting here today have given thought to this. The average person on the street has given thought to this question. And I like to point out that I think it was this quote down at the bottom from Stephen Hawking. We normally think of Stephen or associate Stephen's work with sort of the extreme physics of black holes and the complex mathematics of the early universe. But in the last sort of decade of his life, Stephen was just like you and I, became a little bit more focused on that question. And it's a nice quote that there's from Stephen, that there is no bigger question in science than the search for extraterrestrial life. And like I said, I'm not going to answer this question, but I hope to at least give you some pause for thought on why answering this question is as challenging as it has proven to be over the last sort of 50 years or so. Before though, I just wanted to give you just a couple minutes about where I'm sitting right now. Some of you will have been to Hull before, some have not been to Hull before, but just to give you a little bit of context as to who we are and what it is that we do. And probably the first thing to note, because it is a very common one I get, if someone's leaning over my shoulder on the train or a plane, seeing what I'm working on, they see this E.A. Milne Center for Astrophysics. So the very first thing to say is that E.A. Milne is not the same as A.A. Milne. There's one little difference there in the letters. Arthur Milne, who is from Hull, was not related to Milne, although they do have some interesting sort of parallels in their life. When I moved to Hull, I guess it's coming up on 8 years now, I suppose. One of the first things I did, I had in my mind that when I got here, I was going to try to establish this research center in astrophysics embedded within the physics and maths department. And so I did, like many people do, is I Googled famous people from Hull. It's a very short Wikipedia page, let's say. But one of the names I did recognize in that short list of famous people from Hull was Arthur Milne. Arthur was a contemporary of Einstein. They were actually very good friends. Arthur Milne did a lot of work on overlapping areas of cosmology and research that tweaked Einstein's curiosity. Arthur was more rooted in kind of the classical physics that governs our day-to-day lives, what we call Newtonian physics. He had his own picture as to what the universe was and what it would look like in the future and how it began. it was wildly incorrect physics, but beautifully elegant mathematics. And I think that's what Einstein appreciated about Milne, was this mathematical prowess really stood out, even if the physics was fundamentally flawed. He also did a lot of work on stellar atmospheres, but if you looked at his Wikipedia page, you would see most of it's actually written around his work that he did when he was seconded to the Navy during World War I. He was unable to serve during World War I because he was unrecognized at the time, but it was early onset Parkinson's. So he and a group of astronomers were seconded to the HMS Excellence in Portsmouth, where they were charged with designing the first sort of anti-aircraft gunnery technology. And he came up with a very clever way of using sound, what's called echolocation, effectively triangulating by sound. And, given the south of England, between cloud and fog, a lot of the anti-aircraft gunnery technology that was in place at that point in time had to work on sound rather than by sight. And World War I was really the first war fought in 3 dimensions, where it wasn't just what's happening on the horizon, but what was happening up in the clouds and the fog. And so he designed this beautiful echolocation technique to very rapidly feed information back to gunners on the ground to optimize where they should be pointing their weaponry. So there is a lot on his Wikipedia page about those contributions. But he was also one of the most decorated scientists of the first half of the 20th century, alongside Einstein and a few others. And that's why we used Arthur as our namesake for the Center for Astrophysics here. Around the time that I moved here, his daughter Meg, who's if you can see my cursor, Meg is down in the bottom right there, actually alongside my wife, who's down in the very bottom right, who's a physics teacher. With Meg, she published a biography of Arthur Milne, her father. And if you are interested in sort of the history of astronomy, and maybe one of the lesser known contributors to the history of astronomy, I would encourage you to seek out the biography that his daughter Meg wrote. The center, like I say, we established about 7.5 years ago. It's gone from 0 to, actually it's not even 30, this number is a bit old. We're up to about 40 staff and postgraduates researching everything from the nearby universe, the solar flares and their interaction with satellites, through to the large scale structure of the universe and sort of every scale in between. And not that you would know, but lurking in the back of this group photo when we had the opening of the center was the commander of the Royal Navy, who came up from Portsmouth to celebrate the launch of the center and celebrate the contributions that Milne played to the war effort during World War I and again in World War II. And it's one of these things in passing that I didn't know about until a few years ago, when the 50th anniversary of Apollo 11 crept up. The very first moon rocks and moon dust that came back from the moon in '69, they weren't taken to NASA. They weren't taken to Caltech or Chicago or Princeton or Yale. They were actually brought to the University of Hull. I had no idea about this until various media outlets got in touch with me a few years ago asking for my thoughts on this, and I had to do a little bit of digging around to learn more about this. But at the time, 50 odd years ago, the university had one of the most active geophysics and geological / applied physics groups in the world, and the most advanced and sophisticated equipment. And so those very first little samples that came back from the moon were actually brought here. And I do have over in the corner a little sample of one of those that I take around to schools, including the primary school I was at this morning. So that was an interesting thing I didn't know about the Center, about Hull and its contribution to space sciences. We do use telescopes. We're not nearly as sophisticated as you folks are, and just from looking at the photos, I think it was Keith who you put up the photos. I mean, we're nowhere near as advanced as you are in terms of that sort of level of astrophotography, but probably about a quarter of our effort, it does make use of telescopes for various things. But a lot of the work that we do is based around using supercomputers and high performance computing. That's one of the reasons I moved my group here a few years ago, was the university did invest heavily in supercomputing. And so we do have one of the most powerful, probably the most powerful supercomputer owned by a single university in the country, which has allowed us to do some pretty cool things. And I'll show you something that we've been doing in that front towards the end. And I do have a colleague there who I've mentioned already, that you probably do recognize. Stephen Hawking and I, we have a grant with the UK government that funds the country's national cosmology supercomputer. So anyone who's interested in sort of that extreme physics of how galaxies and the universe forms and evolves has access to that facility. And even though Stephen did pass away a few years ago, we do maintain that connection with Cambridge and have a 20% share of that facility, which again has allowed us to do some pretty cool things. And as Chris was saying, one of the reasons I moved here was, I had the opportunity, if I wanted to go to maybe the more famous universities, Russell Group universities, the Oxbridges of the world. But I've always made my career choices based on where I thought I might be able to make a difference. And Hull is in terms of the various metrics that they use, is the poorest city in England in terms of household income. And so I felt that I wanted to be somewhere where I could make a difference. And so we do work a lot with schools and colleges around the region, all across more or less all across the north of England. It's not about recruiting. It's about trying to, instill that passion and love that we have for the space sciences that everyone sitting here tonight has as well. We're doing about 150 schools and outreach events per year now. We cracked 3 million not too long ago. I think even this month, I look back over January, and I think I've done about 15 events, reaching a couple of thousand in person. And we have a shared ethos across the center to do that. So it is a big part of what we do. And the other aspect, just to finish up on, relates back to widening participation, improving the diversity of the space sciences. We're not alone. Physics, computer science, engineering, there's a huge gender gap disparity, and we have there's no simple solution to these things. They're rooted in sometimes very subtle things that happen when you're in nursery and foundation year, in the early years in primary schools. And so a lot of our focus is on those early years, nurseries, foundation, and the early years of primary, key stage 1, trying to reach out to, in the first instance, our focus was on girls and young women and keeping them excited about the space sciences. I've been incredibly fortunate to have a lot of students who shared that same passion for widening participation, and that's just a subset of them who've really helped transform what we're doing here at the University of Hull. And as Chris was saying, we've actually now tripled the number. When I first got here in 2015, about 10% of our first year cohort were women. Last year it was 45%. This year it's 35%. So right now, I think as far as we can tell, we have the best gender balance across, I think, anywhere in the Western world in terms of people studying physics. So that's more than the research we do, more than the teaching that we do. That's probably the thing that we point to that we take the greatest pride in. And I've got a new generation of students who are helping out, because diversity is more than just gender. It's everything from LGBTQ and BAME. And so I have a new generation of students who are helping out with this program to improve diversity. And we most recently, all of those women who've been helping out were awarded a prize from the UK government, the UK Equality Challenge Unit, for this Changing Face of Physics campaign that's made such a huge difference for our region. So I'm very pleased for them and the work that they have done. It's had a huge impact on what we do here. So I apologize for taking an extra 5 minutes to give you that background, but since it was my first time chatting with you, I wanted to give you a little bit of context to who we are and what it is that we do. And now I'll come back to probably ultimately why you're here, is looking at this question, are we alone? And as I promised at the beginning, probably not going to change your mind one way or the other, but if nothing else, hopefully give you some talking points to think about this question and why answering it is not proven to be maybe as trivial or simple as we had hoped maybe it might be. So one of the first things I do, when I go out into schools and colleges or talking with the public, I get pushback almost immediately saying, look, of course we're not alone. We already have all kinds of evidence that we've been visited, that there is some sort of advanced or not advanced life out there. So again, I'm going to take a few minutes and just look at just a handful of the things that have been suggested as being evidence that there might be something more than just our biosphere out there. Some of them are easily dismissed. Some of them are a little bit more interesting. This is one of the ones I think it might be the most interesting one of all the ones that I'll put up right now. I could talk for hours on this, I could go into UFOs and all kinds of things to chat about, but I'm just going to dip into a couple of interesting ones that have come up. And this one is it's a meteorite. It's the Allen Hills meteorite. There's hundreds of thousands of meteorites that hit us, every year. Many of them are, grains of sand size to things that are, a little bit more impressive in terms of size. This one was discovered it's about 35, 40 years ago on the high Antarctic plateau. It's one of the best places to actually search for meteorites because it is it's clear, it's dry, you've got this pure white relief. And so it's actually quite not easy, but it's much easier to pick out meteorites on the Antarctic plateau for all of these reasons. This one was like many other ones that was picked up, but it was a little bit special. When they picked it up, analyzed it, they realized that this thing, which is a few kilograms in terms of its mass, is not one of the meteorites that's left over from the formation of the solar system, which is 99.9% of the meteorites that land here. They're all fantastically interesting for different reasons, but especially if you're interested in the early origins of the solar system. This one's a little bit different because it comes from the surface of Mars. It was roughly, I think the best guess was about 35, 40 million years ago, something blasted into the surface of Mars, threw up debris. Much of that debris fell back down onto Mars because of the gravitational field of Mars, but some fraction of that debris escaped Mars and spent millions of years wandering around the solar system. And this particular large rock, this meteorite, landed, I think, again, the best guess was probably about 35, 40,000 years ago. And, they zoomed in, they sliced it, they diced it. They knew right away, based on the mixture of the chemical elements and the isotopes, that this thing actually came from the surface of Mars. And what really got their attention was when they zoomed in, as you can see in the picture down below, with powerful microscopes, was they found things that looked like possibly the fossilized remains of some sort of microbial life that might have existed on Mars back when, in the very earliest phases of Mars's existence, there probably was some liquid water on the surface. This rock had seen that liquid water 4.5 billion years ago or so. And the suggestion was that this was evidence that there was some fossilized, some life that existed back then. It got a lot of attention 35, 40 years ago, headlines of lots of newspapers, not just the Sun that you see there, but that was the one that showed up in Google Images when I searched. And, President Bill Clinton, the US at the time, had a press conference on the lawn of the White House, proclaiming, look, our place in the universe has changed. We now know that we were not the only biosphere where life developed. Okay, it's not advanced life that you're going to communicate with, but it was still life. Now, there were a handful of hardy geologists at the time saying, pump the brakes on this. There are things here on Earth that look to the eye like it might be some sort of microbial life, but it has nothing to do with biology. It has what we call an abiotic, a non-biological origin. And we can now look back over the last 40 years and, in retrospect, we realize now that those geologists were right. It got an enormous amount of attention. It was super exciting. The promise that maybe we're not alone. But unfortunately, this one has not stood the test of time. Those handful of hardy geologists actually were proven to be correct. Still very exciting. You can go to the Smithsonian in Washington, D.C., and you can see this Allen Hills meteorite and read a little bit more about the history of it, or just go to Wikipedia. There's an enormous amount of literature about the history of the Allen Hills meteorite. And it's not just the meteorite. And if you want an example of this, if you pick up what's called vermicular, that's what it's commonly called. It's a crystalline rock. It looks, if you just held it in your hand, it looks a bit like quartz. And if you take this vermicular, this sodium, calcium, silica crystal, and you zoom in again with a microscope, what looks to be like a chunk of quartz in your hand looks like this writhing pile of worms that you see there on the screen right now. Just sort of further evidence that just because something looks like it has something to do with life, no matter how persuasive it may look like at first, or as persuasive as maybe the Daily Mail tries to sell you that this has something to do with extraterrestrial life, it's not. It is just a rock. It just happens to look like it's some sort of small microscopic microbial life. And that's just the tip of the iceberg. There's a million other things out there. We have all these rovers wandering the surface of Mars, taking pictures after picture after picture. You can go to the NASA webpage. There's tens of thousands of different images that are in the database there. And yeah, if you take thousands and thousands and thousands of pictures of rocks, eventually you're going to get some that look like it's something to do with life. And these are just some of the famous examples that have come up over the last couple of decades. In the top, you've got a picture of what looks to be sort of a woman sitting on the edge of a ravine on the surface of Mars, sort of resting her arm on her knee, sort of just chilling. Down in the bottom left, you've got what looks to be a frog. The bottom right, you've got what looks to be sort of a floating spoon. What looks to be, here on the left, an iguana. Down in the bottom right, something that looks like a rat. If you've got good eyes, you might see the tail going across the back. And up in the top right, something that looks like somebody's left a bowler hat sitting there on the surface of Mars. And even more recently, I think we've got things that look like anything from coral to a submerged or partially buried skull sitting on the surface of Mars. And again, this, as you say, if you wander around beaches taking zoomed in pictures of rocks, thousands and thousands of them, eventually from the right angle, you're going to find something that looks like it has something to do with life. There's no scale on any of these pictures. Most of them are, centimeter sized tiny little rocks. You can come back years later and they're still sitting there. They haven't changed. So while it may look like life, and every time one of these pictures comes out, it again shows up in the Daily Mail or the Sun as evidence of life on Mars. But this is a well-known psychological phenomenon. It's called pareidolia. We normally associate it with clouds. If you look at it, take enough pictures of clouds or look at enough clouds, eventually you're going to see a cloud that looks like a cat or a dog, a bunny, a train, whatever the case may be. Your brain has the ability to look at these rocks or look at clouds and kind of change what it is and convert it into something that it sort of recognizes. And this is a beautiful example of it. I got two beautiful examples of it here on Earth. One is this really famous one in the Sahara Desert. This is not a tiny little rock. It's a really big one, sort of 4 or 5 meters across. When you take a picture from the right angle, it looks like maybe a hedgehog. But the one I really like is one of clouds, where this one looks just like Winnie the Pooh lying on its back, arms up in the air. So even though it might look like life, it's clearly not life. And so these do get a lot of attention when they come out. But it's really a psychological phenomenon. It's not evidence of life existing on Mars. There is an interesting one that probably many of you have heard of. It's called the WOW signal. This was, probably about 45 years ago or so now. One of these radio telescopes in the US was surveying the sky back and forth, back and forth, back and forth. trying to find evidence that there was some advanced civilization communicating with us using radio waves. They may have been trying to do it on purpose by actually signaling, but it can also just be trying to eavesdrop on radio noise that leaks out of the atmosphere of any advanced civilization's planet. We've been doing it for the last 100 years with the invention of radio. Even if we've not been trying to communicate with civilizations, some of those radio waves do leak from planet Earth, and any advanced civilization within 50 light years of us, they're watching, if they can sift through the noise, they can watch Star Trek for the first time or Star Wars for the first time, because those radio waves are slowly, they're working their way through the cosmos, completely swamped by a lot of the background noise. But in theory, you could eavesdrop whether these civilizations were trying to communicate and find evidence that there was some advanced civilization. When they discovered the signal, this was back in the day when they weren't using external hard drives and pen drives and USB drives. They were just using reams and reams of paper. So they would come in the next morning and sift through 100 meters of these sort of numbers that you see on the screen now. And this combination of letters and numbers, they put a little circle around it and said, wow, this was a radio signal that boomed through for about 2 minutes or so as they were scanning sort of towards the galactic center. They spent an enormous amount of time trying to dissect all of the electronics of this radio telescope that they were using to try to determine, could it have been some sort of electronic noise inside the computers, the detectors, the telescope, the drive motors, whatever the case may be. And, at the end of the day, they said, look, it's such a booming, strong signal that we cannot associate it with any potential internal noise, which is why they wrote wow on it. Now, for the last 45 years, they've scanned all that sky over and over and over again. The signal's never been seen again. But if you wanted to point to something and say, maybe this is evidence of aliens, we cannot with 100% certainty explain what that signal was. It probably was either something internal that they weren't able to track down, or it could have been a ground-based radar signal that goes up to the atmosphere, bounces off. Even 40 years ago, you had lots of satellites flying around up there. So some signal bounced off the metallic surface of a satellite, and that signal came back down into the feed horn of the radio telescope. It's probably something a little more mundane like that than aliens. And even the most hardened believers that there are aliens, advanced aliens out there, do concede that, look, a signal like this, you have to at least see it twice. You can't just pick it out once. So it probably was something besides aliens, but if you want to hang your hat on something that we've not been able to 100% explain away, that would be the one. And like I said, I could spend an entire hour, 2 hours, 3 hours talking about all kinds of different things that have been put forward as claims that there's advanced alien civilizations out there, and many of them you will have seen before, anything from the Nazca lines in Peru. This down the bottom left is the Iron Pillar in Delhi, 5 or 6 meters tall, which has been there for almost 2,000 years, but doesn't rust. And so there was some belief back in the 60s and 70s that this was, had to have been alien technology because it's so hot, it's so humid that it had to rust. But of course, that was just insulting to the Indian ironsmiths at the time, who were fully aware of this and had very clever technology using phosphorus to impregnate the iron to ensure that it didn't rust. In the middle, you've got crop circles. You might ask why aliens who've traveled across the galaxy and they come to planet Earth, why do they always end up in England rather than other countries? And why do these crop circles always magically appear right near major roads? They're not out in the middle of the farm fields. They're always right near the roads. Probably tells you that, these are hoaxes that are being played on you. I do like this one in the top right. Beautiful video of, I think this is over somewhere in the Caribbean, Haiti or Jamaica, I forget now. But if you look carefully, this tree is the same as this tree, is the same as this tree. It was done by a 16-year-old kid in Paris who took a single palm tree and composited it inside of software and generated this movie. It's got millions and millions of hits on YouTube, but it just shows how difficult it is to discern what is fake and what is real. They're all interesting. They all get a lot of attention. They're all fun in some way, but none of them are evidence that there's advanced life out there. But it does sort of come back to where we started. People do want to believe, statistically speaking, something like 70% of the people out there, when you do a random poll, believe and want to believe that there is some sort of advanced life out there. Unfortunately, none of these are evidence that it does exist. So let's come back to this question now and spend the last sort of 20, 25 minutes looking at this question and why it has proven so difficult to answer. So first, a little bit of geography. This is our Milky Way galaxy. If you could step outside of it and look down on top of it, this giant pinwheel, if you turn it sideways, it'd be very thin. You've got roughly 100 billion stars or so inside that Milky Way galaxy. And they're all moving on, assuming your projection is the same, they're all moving nice clockwise circles, more or less nice, perfect circles going around the galactic center. And they're all moving in almost exactly the same direction at almost exactly the same speed. Our sun sits kind of halfway between the center of the galaxy and the outskirts. It's moving roughly 500,000 miles per hour in a nice circle. The stars that are in the outskirts of the galaxy, they're also moving in nice circles at 500,000 miles per hour. The stars towards the center are moving in nice circles, also at 500,000 miles per hour. We sit between two big spiral arms, not much around us. It's nice and quiet. Something we'll come back to in a couple of minutes. But we're all more or less moving in lockstep in the same direction. You got 100 billion stars to play with just in our own Milky Way. Forget all the other galaxies. So you've got, hundreds of billions of planets. So that, it's such a huge number, it's hard to wrap your head around. And it's very easy to understand why most people, when questioned, say, look, there's got to be something out there. There's just, the numbers are so overwhelming, there must be something out there. So what we're going to do is look at these hundreds of billions of potential sites and play a few little astrophysical games and see where the likelihood is. How do those numbers change when we start to look at some of the challenges that life might face in terms of taking root and getting established? So a simple little equation for life, it's, I guess a good analogy is kind of a cooking analogy, where you start with the basic ingredients. In this case, it's the fundamental building blocks. It's the chemical elements. It's, we are carbon-based life forms. So there's carbon, there's oxygen, there's nitrogen, phosphorus, sulfur, all the chemical elements that are the basic building blocks of life. Those are just the ingredients, though. You need to take those ingredients and put them in the right sort of oven, and you need to let them cook for the right amount of time. Little chemical elements by themselves are not life. You need something to bring them together, and you need time for them to form and evolve into something more complex than just individual chemical elements. I'm not going to spend a lot of time talking about what is the right sort of cooking time, other than to say, when planets first form, they're incredibly inhospitable. It takes time for a planet to sort of stabilize and allow even potentially anything to take root. Here on Earth, it took about a billion years or so before the first single cell life appeared. It took maybe 2 billion years for multicellular life to appear. If you want to call it advanced life, mammals have only been around for the last couple 100 million years of the, roughly 5 billion years when we think about our solar system, and Homo sapiens only the last couple 100,000 years. So life doesn't spontaneously appear, because planets really do take sort of hundreds of millions to billions of years for them to sort of stabilize and have any sort of environment for anything to sort of take root and evolve beyond the simple building blocks, the simple ingredients. So I know it's only one planet, but all planets kind of share that volatile history. So there is some time involved before those ingredients can actually cook together to form something more complicated than just individual chemical elements. So let's look at these very quickly. What are the right sort of ingredients? Well, here I'm kind of talking a little bit about advanced life. So Advanced life means you need to move beyond just the chemical elements that we are made out of, the carbon, the oxygen, the nitrogen. You need to make complex molecules. It could be organic molecules, but you need complexity. Any sort of life, no matter what that life is, requires complexity. It's more than just the chemical elements. You need molecules. So we think carbon, even though, again, you could think of it as a bias because we are a carbon-based biosphere and carbon-based life forms, but carbon is more or less unique amongst all the chemical elements. It's a really friendly chemical element. You can take more or less any other chemical element. You can take oxygen. Oxygen, it happily sticks to carbon. You can make carbon monoxide, carbon dioxide. You can stick hydrogen onto it very easily. You can stick nitrogen, phosphorus, sulfur, all the things that we think are important for life. Carbon is very receptive. Other chemical elements, people, I grew up watching Star Trek, so silicon-based life forms. That was fundamental to some of the episodes of Star Trek. Carbon and silicon have some similarities, but silicon is not a friendly chemical element. You stick oxygen onto silicon, you form rock, and you're kind of done. You don't make anything more complex than that. Carbon is unique. You can make wildly complex, elegant molecules because it is such a friendly base element to construct life on. No other chemical element is as friendly as carbon. So there is some logical chemical reasons why we think that carbon is a fundamental ingredient for life. It may not be life like us, but whatever that complex life might be, it needs complex molecules, and carbon is unique for making complex molecules. So we think that's one of the fundamental ingredients. We do think, no, don't worry about that. We also think that water is probably an important component of the development of life. Now, again, it's very easy to say, look, we have a bias, we're not only are we carbon-based life forms, but, we are kind of a water-based life form as well. But water is this magical medium for life to develop in. Those first single cells, whatever they may develop into, those first cells, they're a bit like, you and I, they need to be fed and they need to get rid of waste material. And water is this fantastic medium. It's an incredible solvent. You can put anything into water, it will eventually dissolve. So if you are trying to extract energy from your environment to grow, water is the great medium to use to grab energy from your environment. And it's also the perfect medium in which to flush out any waste material. Now, there's an enormous amount of work being done on what we call astrobiology and astrochemistry, thinking about other mediums in which life might be able to take root. And people talked about, the methane lakes on Titan. Maybe, but, methane is liquid at ridiculously low temperature. It's very difficult to extract the sort of energy you might think that you would need for life to take root. It's not impossible, but it would be incredibly challenging. Water stays liquid over a fairly wide range of temperature, and it has that unique property that effectively no other liquid has. When you freeze water, it doesn't freeze from the bottom. It freezes from the top. You take an ice cube and put it into a glass of water, it doesn't sink, it sits at the top. It's about the only liquid that when you turn it into a solid, it's less dense, so it floats. So when these planets in those first few billion years of their existence are going through, again, very volatile, wild climatic changes, if you're sort of a water-based life form, not only do you have a place to grab energy and get rid of waste material, but if you are going through, 100 million years of an incredible deep freeze, your planet freezes from the top. You still have all the liquid water underneath, which means it doesn't impact necessarily on the development and the evolution of that life. You still have liquid water around you. You can still feed, you can still get rid of waste material. And when the climate sort of stabilizes again, that's okay. It melts from the top. You still have your liquid water. No other liquid does this. And so again, you may think of it as a bias, and you can't argue with that. But there's kind of some logical, biological, and chemical and physical reasons why we think carbon and water are important ingredients for the development of most potential life. Now, so if you buy that argument and you think liquid water is important, you can ask the question, how close can you be to a star? How far away can you be from a star for liquid water to exist? And so in this little cartoon, the number 1, that yellow blob there is the sun. And here's our solar system, not to scale. And there's something called the habitable zone, sometimes the Goldilocks zone. It's not too hot, it's not too cold, liquid water can exist. And so Earth sits right in the middle of that habitable zone. Mars is outside of it now. Probably 5 billion years ago, it was just inside, and there was a brief period of time where there was liquid water on Mars, but there isn't any there now. And the other planets in our solar system, they're either too close, too far away. There's no liquid water. And so you can start to see maybe where I'm going over the next few minutes is we may have started with hundreds of billions of planets. And, every solar system, maybe there are 10 planets-ish around their star. Odds are you're not going to have more than 1 or 2 planets per system that sit in that habitable zone, that Goldilocks zone. Most of the, 90% of the planets that are out there, they're either too cold or too hot. So you've already removed 90% of the potential hosts right away based on the argument if you believe that liquid water is important. So that's one aspect of having the right sort of temperature, the right sort of oven. It's not just temperature, but there's also protection. Earth, we have a magnetic field. And I spent the New Year's up in Finland looking at aurora. Fantastic. We have those aurora because we have a magnetic field. More importantly for us, that magnetic field allows us to hold on to our atmosphere. All of these nasty high energy cosmic rays that would otherwise be blasting into us, some from the sun, some from outside the solar system. We are protected by this magnetic shield that we have, the magnetic field. It's the only reason why Earth has an atmosphere is because we have a magnetic field. Mars doesn't have a magnetic field. That's why it doesn't have an atmosphere. And that's why there isn't any life on the surface of Mars anyways. When you take away the atmosphere, the radiation levels are so intense that it would be very difficult for life to ever develop on the surface of Mars now, just because the radiation levels are that intense. Those first bits, strands of DNA and RNA coming together, they get blasted apart by the intense radiation levels. And you can have a whole other talk on what it would be like to live on Mars. And if you are interested, I've got a TED talk out there that came out about a month ago. There could be life on Mars, definitely not on the surface, maybe subterranean, because then you do have a protection against all of that radiation. But complex molecules organic molecules are not going to form on the surface of Mars because there's no atmosphere to protect it. So other planets in our solar system don't have the right sort of magnetic field that would allow an atmosphere to be retained. So Earth, again, it's a little bit special. Sits in that habitable zone. It's the right temperature, sweet spot for the temperature. But it's also special because it has the right sort of magnetic field that allows it to hold on to an atmosphere that protects you from all the damaging cosmic rays that would otherwise make it really difficult for life to ever take root. So this is kind of another maybe factor of 10 where not every planet has a magnetic field. So we're a bit fortunate that we've got a magnetic field. We also have this big moon that we know and love. It's about 1/100th the size or the mass of Earth, which sounds very small, but compared to every other moon that we know about, it's incredibly large. The other 200 moons or so in our solar system, they're completely inconsequential compared to the mass of their host planet. The moons of Jupiter relative to the mass of Jupiter are in the noise. They're next to nothing. They're, 1,000, 10,000 times less influential than the moon is to Earth. Why does that actually matter? Well, as Earth, as you're no doubt aware, the Earth is tilted away from the sun, the obliquity, 23 degrees. But as we go around the sun, our orbit it's very, very stable. The axis stays pointed at 23 degrees away from the sun all the time as it goes around. And that's the reason why it's so stable, is that we have this big, heavy moon, this anchor that we're dragging around, keeps us very, very stable. The other planets, if we had a really tiny moon, or if the moon was much further away, instead of the stability of the Earth going around the sun. It'd be more like a bowling ball going around the sun. And so you'd be going through wild climatic changes, which is not the sort of stability that you want if you want life to evolve from sort of something microbial to something more advanced, whatever that might be. We don't know a whole lot about exomoons, moons around other planets and other planetary systems. But again, this is not what you want to hear. If you want to think that life is common, you don't want too many special things lining up together. We've already special in that we have the right temperature. We're special in that we've got the right magnetic field. We're also special in that we've got the right sort of moon that gives us long-term stability. All of these things are working in the direction of us being a little bit special. And we're still learning about planetary systems around other stars. We've discovered, I don't know what the numbers are now, 5,000, 10,000 planets around a couple of thousand stars. Again, there's hundreds of billions of them out there, so it's just the tip of the iceberg. If we take the numbers as they stand right now, the 10,000 planets that we know about, around several thousand suns, stars, our solar system looks really different from all the other solar systems. If I took all the other solar systems and made, this sort of if I laid down where the 10,000 planets that we know about sit on this little cartoon, 99.9%, almost every one of them sits kind of around where Mercury and Venus sit. So some of that is probably just an artifact of the way we've discovered planets. But if you took the data as it stands right now, every planet that we know about inside of the Milky Way is butted up really close to their host star. And that is not what you want for life to develop. If you're the distance of Mercury or Venus, you're getting blasted with radiation. It's too hot. Life is not going to develop around the planets that we know, the vast majority of the planets that we know about right now. So again, this is just another little piece of the puzzle that works in the direction of bringing down what used to be a really big number. You lose 90% because of the wrong temperature, 90% because they don't have magnetic fields, 90% because they don't have a stabilizing moon. Maybe you lose a bunch more because they're all butted up way too close to their host star. All of these work in that same direction of bringing the number down. And it can take you from maybe hundreds of billions of potential hosts, hundreds of billions of stars that might have advanced life around them. It brings you down to tens of millions. And that, still a big number, but, it's a lot smaller than what we started off with, hundreds of billions of potential sites down to maybe tens of millions of potential sites. It's more than just the sort of things I've talked about. I mentioned right at the beginning, the sun sits between two spiral arms. There's not much around us, and that's good. We don't get blasted with things left, right, and center all the time. We're moving at almost the same speed of the spiral arms. Now, most of the action in the galaxy is in those spiral arms. Most of the new stars that are forming, the gas, the dust, the junk of our galaxy, most of it is in those spiral arms. But we're not moving at exactly the same speed as the spiral arms. Every, 100 million, couple 100 million years or so, we actually catch up and pass through the spiral arms. So we go from a region where there's not much around us to a region where there's a lot of stuff. And when you do that, you get a shock. You get a kind of like when you're driving on the motorway, there's air inside the car, there's air outside the car. You stick your arm out, you feel that shock from the wind. Now, this is not a wind, but it's still a shock, but it's a gravity shock. You feel the gravity of all the objects. Where we sit now, there's not much around us, so we don't get influenced by the gravity of all of these objects. When you go into the spiral arm where there's lots of stuff, you get shocked by the fact that there's so much stuff around you. You feel the gravity, the influence of those objects around you. And I guess the analogy I've used before is kind of one of these aerial swings. If it's nice and calm, it's spinning around, everything is symmetrical, going in nice little circles. If you get a short, sharp gust of wind, that nice symmetry gets broken. And if it's a really strong, short, sharp gust of winds, then these things can run into each other. And something very similar can happen with a gravity shock rather than sort of the wind shock that I'm talking about there. And as we pass through the spiral arm, you get shocked. And what happens is some of the stars that you encounter are not moving in perfect circles around the galaxy like I talked about. There's so much junk around that they get nudged out of their orbit. And this has happened, and it's happening right now. This is one star in the sky. It looks like every other star. It's called Gliese 710. It's about half the size of the sun. It's not moving in a nice straight or nice circle around the galaxy. At some point in the past, when it went through a spiral arm, just like we do, it's got nudged from that nice circular orbit. It's now blasting straight towards us, like, it's like a bullet coming from the barrel of a gun. It's coming straight towards us, 30,000 miles per hour. And in 1 million years, this star is going to pass through our solar system. So if you're around in 1 million years and you look up in the night sky, there'll be 2 stars. This one won't be quite as bright as ours, but it'll be the second brightest thing in the sky. And it's not going to get down to the inner part of the solar system. So little circles you see there to the left are the planets that we know and love. And then in the middle, that's zooming out of the solar system a little bit further. And then the big picture on the right is zooming out even further. All the planets we know and love are in the little white dot that you might see in the middle. But we're surrounded by this thing called the Oort cloud. It's got billions, maybe even trillions of comets that are sitting in there. And this star in 1 million years is going to pass through that Oort cloud of comets. It's going to shake loose many of these comets. And the best guess is something like 10 million or so comets are going to get shaken loose. Some of them are going to get shaken loose and fly away from us, but the majority of them are going to get shaken loose and come raining down to the inner part of the solar system where we are. Now, fortunately, the solar system is mostly empty. Most of these millions of comets are going to miss us. But all it takes is, one, we see this around other stars. We know other stars have got Oort clouds, and every once in a while they get shaken and comets come raining down to the inner part of the solar system. Again, most of them will miss us, but all it takes is one big one. Those are, 10 to 50 mile diameter ones to actually hit us. And, it's not just us. We've got Jupiter. Some of you might remember, what was that? Almost 30 years ago, I guess, when Shoemaker-Levy came into the inner part of the solar system and got hoovered up by Jupiter. And we're a bit lucky because we have Jupiter. It's this big, heavy gravitational hoover that hoovers up a lot of these comets before they actually make it down to the inner part of the solar system, where they may wreak havoc on the planets in the inner part of the solar system. I can probably just say in passing that most of these other solar systems we know about, the big planets like Jupiter, they're actually really close to their host star. We're, again, a little bit special. We've got this protective shield in the shape and the form of Jupiter that's further away from the sun. It's not a perfect barrier, but it is a partial barrier to protect us from some of these comets that come in. So we're not alone. Other planets see the impact of these sorts of comets, but we're lucky we've got Jupiter to partially protect us. And look, this happens every once in a while. We do get these big impact events. Sometimes it can be comets, sometimes it can be asteroids that have been shaken loose, but these things do happen. 65 million years ago was the last big impact event. Still, debate as to whether it was an asteroid or a comet, but these things do happen. Now, it didn't wipe out all life on Earth because we're sitting here tonight having this chat. Now, if you ask the dinosaurs what they thought about these sorts of things, they would probably have a different perspective from us. But these things do happen. And 65 million years ago, 90% of the species on Earth were wiped out by these things. These things happen quite frequently in other places in our Milky Way galaxy. So it's not unique to us. These are challenges that life must face. And as I say, we've been lucky. We're still here today. But in some sense, we've been very lucky that we've not been wiped out by one of these mass extinction events completely. I looked up this not too long ago. The best guess is if you are around in 1 million years, there will be something on the order of a naked eye comet. We've been talking earlier about the current comet, but a new naked eye comet will appear, I think, once per month for about 1 million years. So about 10 million naked eye comets, if you're around, will be covering the sky. If you like doing astrophotography of stars and galaxies, it'll be a terrible time to be around because the sky is going to be absolutely covered in comets. If you like taking pictures of comets, it'll be a great time to be around. We'll probably have the disembodied head of Elon Musk will still be around, providing some sort of protective shield, or Bruce Willis, if you've seen Armageddon, will still be around doing something to protect us. This is something that, you know, if I was putting hand on heart and saying what's going to wipe us out, well, it'd probably be us that wipes ourselves out. But in an astrophysical sense, if something is going to come along and take out planet Earth on a relatively short time scale, it'll be 1 million years from now when our sky is completely covered with comets whizzing by us at high speed. So these things do happen. It is something we happen to be around in 1 million years. We need to have the technology to protect us from that. And it's not just, you know, one of the final things to say, it's not just these sorts of cometary events and things that happen when you get shocks going through spiral arms. You have to worry about other stars exploding nearby you when you pass through spiral arms, because that's where most of the big stars that live fast and die young and explode spectacularly are born. So this is, you know, a typical what we call supernova remnant. If you're traveling at the speed of light, it would take you about 30 years to cross that. And there is a lot of debate going on in astrophysics now as to how close you can be to an exploding star before it evaporates your biosphere. You know, these things are great. I mean, everything that you can see right now, all the chemical elements that we are made out of came from these exploding stars. So they're powerfully important in terms of the development of life, since carbon and oxygen and nitrogen, phosphorus, sulfur, everything comes from these sorts of stars. But they're also very powerful explosions. And just like an explosion on Earth, you know, if a nuclear weapon goes off on the other side of the Earth, you're not going to notice it where we're sitting or where you're sitting in Hereford. But, you know, if a gigantic nuclear weapon goes off in Worcester, you're going to be aware of it. And it's the same thing with exploding stars. The best guess is if you were near the edge of this, which is, you know, roughly, I don't know, say 30 light years away from the center of one of these exploding stars, when that shock washes over you, that would wipe out everything on Earth and destroy your biosphere. Now, we're fortunate because, again, we sit between spiral arms where there's not much around us. But 10 million years ago, a star did explode near us. And I placed the Earth up in the corner there, about 100 light years away. This happened 10 million years ago. It was far enough away that by the time the shock rolled over us, it was not strong enough to evaporate our biosphere, but it did leave a thin layer of a radioactive isotope. Gory details don't matter. It's called iron-60, a super thin layer of iron-60 spread across planet Earth as this thing washed across us. But if we had been sort of a factor of 3, close 30 light years instead of 100 light years, best guess is it would have wiped out all life on Earth 10 million years ago. And again, we wouldn't be having this conversation. These sorts of things are things that life on whatever planet has to deal with. Another one of the astrophysical challenges that kind of works against the development of advanced, again, whatever you want to call advanced life. Actually, I'm not going to worry about that one. So let's just kind of bring some of this together now, this habitable zone that Chris mentioned at the very beginning. You know, if I take all of these things together, where are the best places in our Milky Way that in a statistical sense might allow the development of advanced life? So you need the building blocks, what we call metals. You need carbon, you need iron if you want to make planets that life can develop around. Far out in the edges of the Milky Way, you don't have enough metals for these sort of rocky planets to form in the same way that they can form in the inner part of our galaxy. You need stability. You don't want to be racing through spiral arms constantly, getting pummeled left, right, and center. You want stability, and you don't want to be too close to exploding stars. So the center of our galaxy is filled with exploding stars. It's such a nasty environment that's not the right place to look for advanced life. And this is part of the work that we do here with my group. It's not the primary thing that we do, but we make use of these sort of high performance computing simulations of how galaxies form and evolve. And then we can wander our way. Both of these simulations eventually settle down into something that look a little bit like the Milky Way. And we can wander our way through it and look, in a statistical sense, where is the best place inside of these galaxies to find life? Like I said, being too close to the center, you're getting blasted by supernova. Too far away from the center, you don't have enough building blocks for sort of rocky planets, terrestrial planets to develop. We want to be kind of in the middle where we are, because we are moving at more or less exactly the same speed as the spiral arms. If we were further out in the galaxy or closer to the middle of the galaxy, you get pummeled by the spiral arms very regularly. We're in a special place, again, called co-rotation, where we move at almost exactly the same speed as the spiral arms. So it's another one of those special things that you don't want to hear about if you want to believe that life is common. But it is something that again, is a little bit of and just one small little piece of the puzzle that suggests maybe life isn't quite, or advanced life maybe isn't as common as we might like. It's another special thing about where we sit that has allowed life to develop. And again, it's a whole other talk, won't go into it, but the simulations I just showed you are using a technique that was invented by astronomers about 45 years ago. Called SPH, smooth particle hydrodynamics. It's the laws of fluids, how fluids and gases move, how they change when you heat them up and when you cool them down. It's used in all kinds of areas of science nowadays, from erosion studies to natural disaster simulations to the design of artificial hearts. McLaren uses it for developing Formula One cars, the design of wind turbines and turbine blades. All of these things are using astrophysical software applied obviously to something very different than what I've just described. But it links into why people who study physics and astrophysics actually have really high employability, is because, I can teach them to do stuff in astrophysics, but they can take those skills and move into any of these sorts of areas, simply because the underpinning tools that are used to do the sorts of simulations I've talked about are used in all of these different areas. And all these other ones as well, aerospace, automotive engineering, all using astrophysical software, again, applied in a very different regime, but it makes it very easy to cross those disciplines and ensure that physicists and space scientists have high employability. So I'll pull everything together now and wrap up. Started off with, in our Milky Way, admittedly, it's only one galaxy, but we'll stick with that one, something on the order of 100 billion stars. So it's a lot of potential sites for life to develop. Probably about 1 in 10 are the right sort of stars. I probably didn't talk about that one when I should have. Stars that are heavier than the sun, maybe 2 times, 3 times, 10 times, 50 times heavier than the sun. They burn through, they live fast, they die young. They're gone before, in time scales of a few 100 million years. There's just not enough time around heavy stars for life to develop. Stars that are, half the mass of the sun, there's lots of them out there, but they're much cooler in their temperature, which means the planets have to be butted up really close for liquid water to exist. And the problem is they have to be so close that they're getting blasted with radiation. So maybe you might have liquid water, but the surface is just untenable for the development of life, because the radiation levels are so high, it's going to blast apart any sort of complex molecules before they ever have a chance to develop into anything. Still, 100 billion stars. So yeah, maybe 1 in 10 are the right sort of stars. Probably about 1 in 10 are kind of in the right place in the galaxy, not too close to the center of the galaxy, not too far away from the galaxy, at what we call co-rotation, where you're kind of moving at the same speed as the spiral arms. Best guess is about half of the stars out there have planets around them. Not every single star has got planets, but most of them do. Again, we're getting to kind of stats that we're working on right now. Maybe 1 in 10 have a rocky planet, terrestrial planet, that sits in that habitable zone, that Goldilocks zone, that sweet spot where water might exist. Now we're getting more speculative. Maybe 1 in 10 have a magnetic field that allows an atmosphere to be retained, which will allow life, whatever that life might be, to take root and be protected from nasty radiation and cosmic rays. Maybe 1 in 10 have a stabilizing moon that gives you that long-term stability, climate stability that you need for whatever that life might be to actually take root and evolve. And you can see, you start with a big number, but you start throwing away 90% here and 90% there and 90% there. And it kind of takes you from, 100 billion down to maybe 500,000 potential sites for advanced, civilizations. Again, it's a big number, but it's a lot smaller than what we started with. And that's sort of being optimistic with some of those numbers. If you're a little bit more pessimistic on some of those numbers, it's not difficult to get down to, that level of a few hundred or 1,000 or so. you're starting to get down to sort of uncomfortably very small numbers for potential advanced civilizations. And you can ask the question, and it comes back to, Chris had it right on the slide at the very beginning, the Drake equation. As you move through the Drake equation, which kind of is a little bit what I've been talking about here, there's 7 or 8 terms in the Drake equation. Ultimately, it works out how many advanced civilizations might be out there. And as you move from the left, you start off with things that are sort of well-known. And then as you move to the right, you move through various astrophysical things into chemical and geophysical things. And then the last term in the Drake equation, which kind of gives you this rough idea, it's a fundamentally flawed equation, but it's useful to frame sort of the discussion, is maybe there are 500 civilizations if you're a pessimist, or 500,000 if you're an optimist, looking at the numbers I just said there. You might ask, well, how many are out there right now? It kind of depends on how long an advanced civilization survives for. We've been in a quote unquote advanced phase, by which I mean, the ability to communicate, whether again on purpose or not. We've had rough radio for about 100 years. So we have been communicating or sending out radio waves through the cosmos over the last 100 years or so. And during that 100 years, we've almost managed to wipe ourselves out multiple times for various different reasons. But let's just say we somehow managed to get through what we've done over the last 100 years. And you can ask the question, let's just say an advanced civilization can live for 20,000 years. And then you can ask, well, if that is the case, how many advanced civilizations exist in our Milky Way today? And the depressing number is 1. That could be us. So you start with a really big number as potential sites for advanced civilizations. The astrophysical arguments and chemical arguments that I've made take you down to the hundreds of thousands, or even the hundreds level. And then that sociological, the socio-political argument can actually wipe out everything and bring you down to a really small, depressingly small number. So that is just something to bear in mind. You can poke holes in probably each individual step along the way, but hopefully, if nothing else, you get the gist of what I'm trying to argue, that individually, each one of these, you can argue about the numbers. But when you start to string these sorts of things together, it might mean that life isn't quite as common as many of us hope it will be. And, despite everything I've just said, which might be sort of a depressing, somber conclusion, I do want to believe that there is something out there. And I do believe that there's something out there. Where are we going to look? And then this is where I'll end. I'm not convinced in my lifetime that, we're going to be communicating with radio emitting advanced civilizations out there. Where might we find life? If it's going to happen in my lifetime, it's probably going to be closer to home. It's going to be inside of our own solar system. It's not going to be the surface of Mars. Like I said, it's too hostile. But there are some subterranean places. The moons of Jupiter and Saturn, Europa and Enceladus, they're basically gigantic ice moons, 200-mile thick layers of ice. Underneath that is an enormous ocean of seawater. It's ridiculously salty. It's hard for us to imagine anything that could survive in just how, the high levels of what we call salinity. But every once in a while that ice cracks and you get water geysers that shoot up, which is what you're seeing there on the right. There is a mission that NASA is sending over the next decade, Europa Clipper mission. I think it's actually supposed to launch next year, or 2025. And it's going to fly through these plumes of water and scoop up this salt water. We're not going to find aquaman or piranhas, but maybe we'll find some sort of microbial life that is sitting there. I'm not optimistic, but if we're going to find life outside of planet Earth in my lifetime, I'm going to guess that's probably where it is. And I think that is a very good place to end, because it's now 1:15, and I'm sorry for running an extra 5 or 10 minutes there, but hopefully you've enjoyed that. Hopefully picked up a few things. Happy to take any questions that you've got.
Wow. Thank you, Brad. Thank you very much indeed. That's another wow moment there. No pun intended, but that was a wow talk. Yeah. I must admit, I'm not a professional. I'm not a scientist, and I'm not even familiar with the stats. But I know the basic numbers that go into how many stars there are and the likelihood of how many planets there are revolving around each star and how many galaxies there are, potential stellar systems. And I realized that the numbers can be whittled down, and whether you use the Drake equation or the Gibson equation, that seemed to me, you've got your own equation going there, but it's the same principle. You're whittling down all the probabilities until you get down to it might be depressing, but it's the way it is. And
it's the way it is. Yeah.
When I was a kid, I firmly believed there were aliens out there in the sort of traditional sort of Hollywood sense, sentient beings, bug-eyed and very intelligent, who could crush us, merely by sending their death rays at us. Yep. And as I got older, I thought, well, the reality is that probably these are not so frequent. And then I swung the other way and started thinking, well, we're possibly completely alone because of the uniqueness of our situation. And I think part of it's science and part of it's almost philosophy today. Yeah, nobody really knows. And I don't want to bring religion into it, but I'm not a believer, and I'm not going to bring God into it. But you could, if you at one extreme, you could make the argument, well, given all these incredible coincidences, the stabilizing influence of the moon, the Goldilocks zone, the fact that that's a rocky planet, that we've got a nice, lukewarmish star, not too hot, not too cold. We're in a non-gravitationally shocking part of the galaxy, as you explained. Put all that together, say, what are the chances of that? Well, they seem very, very remote. And I don't know whether there's a word for this, but I've come up with the solipsistic theory. This is where you think of like, I don't know, let's say 10 million people do the lottery. Now, you don't have to be a mathematician to say that if there's only one prize, you've got a 1 in 10 million chance of winning. But then somebody wins and you look at them and say, wow, what were the chances of that? Well, the chances were 1 in 10 million, but they've done it. They are the lottery winner. Yeah. And they then look around at everyone else and say, haven't you won it? Haven't you won it? Why haven't you won it? And of course, we could argue that if there were to be one unique, absolutely unique instance of life not just in our galaxy, but in the universe, that one unique instance would say, why me? It's too improbable. But if there were to be just one, we would be asking it. I mean, that's one extreme, but it's not scientific, but it's philosophical, and you can make an argument. And I like to think we're somewhere in between.
There's an enormous overlap. I mean, there are entire research institutes out there that link sort of what the astrophysical side of things, but there's one in Oxford, there's one up in Scotland that link philosophy and theology, and even they've got groups who work on what would be the socio-political, economic implications if we woke up tomorrow and realized, oh no, there's advanced civilizations out there. What would be the impact? People are thinking about this from completely different perspective than what I'm thinking about, because it does touch on, exactly as you say, it does tickle the edges of philosophy and sociology and all these different areas, which I think is why it does resonate with so many people, because it does all of those things.
Absolutely. Anyway, I'm getting ahead of myself. I was so excited by your talk. I had to get that in. So first things first, from all of us, from the bottom of our heart, a really big thank you, Brad. That was wonderful. And it's difficult on Zoom, but we can either clap hands or show a virtual clapping hand. Big round of applause for Brad. Fantastic.
We are very lucky in the space sciences and astronomy and astrophysics, because we've got 250 astronomical societies spread around the country. And I talk to other scientists. There aren't many amateur nuclear physics societies out there, and you probably don't want to be interacting with amateur nuclear physics societies anyway. But we do have this unique ability to reach everything. Every kid, when they're 3 or 4 years old, they love space. We've got these societies doing amazing things. So we are really spoiled by being able to interact with all of these different societies. It is one of the real joys of the job. And I'm not sure what I would do if I was in a different science that didn't have, that same way to resonate with the full spectrum from 3 to 103. So I'm very fortunate that I get these opportunities to interact with you folks.
Yeah, I think we got a couple of members here who are 103 actually, but
I feel like it right now.
but no, that comes across quite apart from your obvious professionalism and the rigor of your own discipline. It's very obvious that you're very passionate about, about the dissemination and passing on your enthusiasm for the subject and reaching as many people as possible. And I think I'm getting the impression that you're as proud of that as you are of your academic achievements, even. And
yeah, I mean, if you'd asked me 10 years ago, no, I mean, in fact, I don't want to bore you with all this, but when I moved I was in central Lancashire, eight years ago when I moved. I think up until that point, Mike, I was 10 years in Australia, I was 10 years at central Lancashire. I was like, 90% of the academics, I was focused on my applying for research grants and my teaching, and it was me, and developing my group, and that was the most important thing. It wasn't until I moved here that I sort of became the head of department and head of this, and started to think a little bit more. I never, I look back over my track record. I didn't do any outreach or engagement 10 years ago. And I think when I first started here, it was probably initially driven by mundane things like recruitment. I'm going to go out and I'm just going to talk to year 12, year 13 students, and that's the only thing, because it's all about recruiting and bums on seats. And that's probably how I sort of dipped my toes into it, was that. But then that it's far and away the best part of my job now. I love doing this, which is why I've been able to ring fence the time, and I've got a very forgiving wife who allows me to do all of these sorts of things. And it's hard for me now to think back on that time when I was singularly focused on sort of the research and the next paper and the next grant.
Yeah,
so it is the thing that drives me now. That's the part that gives me the joy in my job, is going into school. This morning I was talking to 100 year one students, and it was fantastic. And then in the evening, I get to come and talk to you folks.
Well, we feel very, very privileged and lucky to have been able to grab you. So that's great. Okay, I've talked enough. Let's hand over to the floor. I'm sure some people have got some interesting comments and questions. Anyone got a question for Brad?
Yes. It's Sue Olver. Can you hear me?
Yes, indeed.
Yeah.
Yeah.
Hi, Sue.
Yeah. Hi. It's the moon, of course. As you know, it's moving away.
Yes.
And there's part of that moon that's fixed, and a part of that moon on the dark side has been so bombarded. Now, I reckon that must have protected Earth a lot. What are your views on where the moon is going to be going in the next 10,000 years? Because I've got a feeling it might be not so great.
I think that the time scales are a bit longer. So I think we're okay for the next, 10,000 years or so. But yeah, if we come back and have this talk I do have a talk on this, on how the universe will end, and I do walk through the timeline. And so now I forget the numbers, but it's drifting away at whatever the number is, a centimeter a year. I forget the number now. But when you come back in, it's X million years or so. While I'm talking, I'm going to try and pull up the numbers so I don't give you completely bogus information. But yeah, in X million years, whatever that number is, which is, I'm opening up right now. Let's see if I've got this one, because
I think a centimeter a year is about right from what I remember.
So let's see, what do I got here? 250 million years from now, the moon will be 6,000 miles further away. Not that these numbers really matter, but what that means is in 250 million years, so we are talking millions, not thousands, but 250 million years, our day will be 25 hours, not 24. So that's one of the things that it impacts on the length of our days. And then 3 billion years from now, so the sun will be coming towards the end of its life. So we're talking, a long time from now, 3 billion years from now, it will be 75,000 miles away, further away than it is now. So, roughly 25% further than it is now. The main point for that is, at that point in time, that's when it will stop influencing sort of the orbit of us. So it'll be far enough away that it won't be a stabilizing influence on us. It will always be a tiny little bit of a protector, but it's still quite small compared to Earth. So yeah, every once in a while it will pick up, exactly as you say, it provides this a tiny little protective barrier, but its gravitational effect on hoovering up comets and things is very small. But you don't have to worry so much until probably a few billion years from now. At that point in time, the Earth becomes more like a bowling ball again, because that stabilizing influence of the moon doesn't affect us. I couldn't remember the numbers until I just pulled it up right now. So thank you for asking that one, Sue. It's a good question.
Yeah, I don't think we need to worry about that too much. And from what you were saying in your talk, Brad, the raining comets are going to come down before that anyway.
I presume if we happen to be magically around in a million years, yeah, probably we'll have some sort of technology that, I don't know, deflects the, we had the experiment last year where NASA was, trying to deflect the asteroid. So, a million years buys you some time before you have to really lose sleep over it. Unless some magical mystery one shows up that we haven't had any forewarning about, then we don't have the technology right now. But in a million years, presumably, if we're still here, we'll have that ability to deflect them enough that they're not going to bother us. I don't know.
Yeah. Okay, somebody else?
No pressure if you don't. It's okay. You don't also know how to reach me if you ever want to email me. Also, yeah, if anyone's a teacher or governor, got kids in school there, I'm more than happy, to come into lots of new different schools. I've been out I've been down south, as far south as you can go, and Dorset, and done some talks there. I was out in Cardiff not too long ago giving some talks, which so I got to pass right by Hereford as I was on my way out there on the train.
That's great.
If you do have a connection to a school, drop my name. I'm happy to make the trip.
Yeah. Well,
Brad, can I just ask a quick question? Thanks very much
for the
talk. I just wondered, I take it probably that your view is that there may very well be life around, if not intelligent life.
Yeah, I think, if you'd asked me 10, 20 years ago, look, I would have said, yeah, the place is teeming with aliens, and I grew up a sci-fi fan. I wanted to believe that as well. I mean, I just assumed that would be the case. And I guess I've just gotten maybe a little bit more cautious, or step back on the galaxy is teeming with advanced life. If I had to put hand on heart, you did a lie detector or something, I guess I'd come down on the side of, I'm not convinced there's any advanced, again, we can have a debate on what that means, but some advanced communicative civilization out there. I'm still 100% sure that there's life out there. It just may be some sort of microbial sludge, but yeah. I hope I'm wrong. I think
you might expect a biosignature detection in your lifetime, possibly.
I hope so. So this is it. I've got one of the staff members here who I would encourage you to invite for a talk. Just drop me a line, Chris. David Benoit, who does a lot of society talks as well. He's a wonderful speaker, and we have a PhD student right now who is working with us on identifying potential biosignatures in the atmospheres of exoplanets. It's beautiful work. He's also got some really nice talks on ocean worlds and what they might be like. But yeah, if you want to get into a little bit more of the details of if there is something out there, what might the signature be? Because we will, over the next 10 years with all these new facilities, we will be able to really dissect what the atmospheres of some of these planets. We've already been able to do it with a few planets now. It passes in front of the star. You take a spectrum and you can see as the starlight passes through the atmosphere of the foreground planet. We've found ones that are, laced with all kinds of sodium. There's no life there, but we can detect that atmosphere is completely filled with, sodium. But there are other biosignatures that might, might exist. It could be chlorophyll, something to do with plant life, maybe. could be some other carbon-based organic molecule. So it's a hot topic. Lots of people are working on it. But if you want to explore a little bit more about these biomarkers, biosignatures, and the potential for detecting them, get David Benoit to come give a talk. He'd be great.
Well, I'll definitely be back in contact with you anyway, because we'd love to invite you back either.
Oh, absolutely. Yeah.
Either, virtually or in person. That would be great.
Yep, I'll do
maybe next season. We book out well in advance. So
yep.
You're a busy guy. So
no, absolutely no. There's always time for this. I love it. Love it.
Anybody else got a question?
Could I just ask one question?
Please.
Brad,
yep.
I work with children and young people who struggle with their mental health, and many of them struggle to leave the house. Do you offer any kind of online or aware of any kind of online forums or where young people might interact, but on this subject?
Yeah, I mean, I admit I'm not I'm not an expert in these sorts of things, but certainly, over the last, because of COVID, I was still doing 100 school events a year, even during COVID, but they were all online. And some of them, some of them are, they're, SEN students who are in various, depends on the school. Sometimes it could be one-on-one, could be just teacher and a student, could be just me with the parent and the student. It could be a class. It can be, a brief punchy little presentation, and then just a Q&A where they can ask me anything under the sun that they feel comfortable in asking. So I'm certainly adaptable to whatever it is that the needs may be. If we're going into some of the SEN-based schools, we have a planetarium that we take in sometimes, and because I've got some great students who run a mobile planetarium, and so we'll take that into schools. I mean, and any school, but they have adaptable shows that do adapt to the sort of the needs of the students, whether they're SEN or not non-SEN. They know exactly what it is they're doing and how to reach and appeal to the broadest spectrum of the students that are out there. So if there was some special desire to do something, I'd interact with the teachers and talk to them about what are the sort of things that they would like. Do they want a Q&A? Do they want a presentation? Online ones, I've done lots of them, and obviously doing it in person is always better, but it's the way the world works nowadays, so you adapt as best you can. So yeah, just you can follow up with me offline, send me an email, and we can arrange something.
Oh, thank you very much. Thank
you, Nikki.
Yeah, just do it through me, Nikki, if you want.
Yep.
Okay, anyone else? Anyone? I've just got one more then, just one sort of semi-technical. You mentioned the proximity, the exoplanets, Brad. You on that diagram, not to scale, of course, but you showed the Goldilocks zone, how most of the planets we've found are extremely close to their host stars. Okay, the host may be it could be a red dwarf, or it could be a hot star, but basically they're very close. They're sort of closer than even Mercury, or but they're in that kind of very, very close. But I can't remember how many techniques there are for detecting exoplanets, but I think the transit system is certainly one of the most popular, and even allowing for the fact that it misses everything that isn't in the line of sight. I think to be sure with the transit, you need several passes. But wouldn't that, the transit method with multiple passes kind of implies that most of the samples are actually short orbit, small orbit.
I'm 100% sure.
There could be lots of potentially transit planets. They're in the line of sight, but they're in such large orbits that we're only going to see it once every 200-300 years, a la Neptune or Uranus. So could that give a false perspective of how many planets?
There's far clever people than I trying to understand what they call the the selection effects, the biases that come into play exactly as you describe. And I've seen arguments both ways that my gut feeling is that yes, we are missing a lot of the long period distant planets for all the reasons that you say. In theory, if you are using the radial velocity technique, where you take the spectrum of the star at incredibly high spectral resolution, then it doesn't really matter. You don't have to see the planet passing in front, because as it moves around the star, you know, it causes the star to wobble just that tiny bit.
That's one of the other main ways.
So that is one of the ways that it's a lot more difficult, because the stars have to be much brighter to get the sort of spectral resolution with a high signal to noise that you need to see these things moving at, you know, meters per second level, not you know, what you can do with low resolution spectra. So it has been done. The very first work on, you know, the ones who won the Nobel Prize, in fact, that's a whole other different story, but I went to do my PhD in Vancouver, because right around the time I was thinking about my PhD was the first work that came out on using exactly this, precision radial velocities to search for planets. And I thought, this is what I want to do. I want to be a discoverer. I want to be on the leading edge. This sounds great. And this technique was invented in Vancouver, a big article in Scientific American. And that's why I ended up going there. I got to Vancouver and started my project on that. And within a few days, I thought, this is the most boring thing I have ever worked on in my life. It was incredibly tedious, noisy data, just sifting through noisy data, trying to find this. It wasn't swashbuckling discoverer of planets, which is what I pictured my PhD to be. So that's when I jumped ship immediately and went into liquid mirror telescopes. Now, it was career-wise, probably was a mistake. But looking back now, I feel for the team in Canada, because they actually did detect the first extrasolar planets. But being Canadian, when they wrote the paper, they were so polite about it, saying, well, maybe it's a planet, maybe it's not, who knows? You know, Canadians, you know, every paper had like a question mark, you know, is this a planet with a question mark? If it was an American who wrote it, it would be a blunt statement saying, we discovered a planet. And that's what happened a couple of years later. The people who won the Nobel Prize, Marcy and Butler, that was what it was. You know, they won the Nobel Prize for using precision radial velocities for discovering planets, even though, and I've spoken to them afterwards, and they said, yeah, I mean, we feel bad about it, because it was these Canadian guys who really are the ones who discovered the first one. We confirmed it, you know, a couple of years later. So that technique that one bypasses some of the issues that do exist. I mean, you still need to monitor for a long period of time to see the wobble, but you're not quite as susceptible to missing things in the way that you are with the transit technique.
Transit method, yeah. So
yeah, I'm sure the stats are, no matter what experts say, I'm sure the stats are biased, and we're missing a lot of these ones. So my numbers will increase in terms of potential sites, because I'm taking the numbers at face value, but I'm pretty skeptical. I'm pretty sure we're missing a lot of those, exactly for the reasons that you say.
Right. Well, we're pretty near to wrapping up, but we still have pretty much everyone still with you. So I'm just one more thing then. I did mention at the very beginning that the other week, just by browsing idly through YouTube, I came across liquid mirror telescope. I'd never heard of them. And it was something to do with, it goes back to the 18th century, someone with a centrifuge and mercury, and it was naturally forming a parabola, and it sounded very complicated, but in theory you could use mercury at the time is what they used. Could you, Brad, I'm going to sound like a Radio 4 presenter, but in 2 minutes, could you just explain to us what you did and what the liquid mirror was and how it worked? Is that unfair?
It is. That is exactly more or less as you described, Chris. If you take any fluid, any liquid, and you spin it, it naturally takes the shape of a parabola. And it's how big mirrors are. A lot of big mirrors are made this way as well. They, you know, they take molten glass and they spin it, and then they let it cool down, and you naturally take the shape of a parabola. So it cuts down all the figuring of the mirror that you have to do by just taking into account that. So we're what we did was we built a 3-meter telescope using something that we did spin cast, but we spun cast something that was polyester resin. So that gave us roughly, you know, to a millimeter or so a parabola, and then you put a couple of millimeters of liquid mercury on and spin it, and you get a beautiful, perfect. I mean, if you stand there right beside it, you can't tell it's moving. It's just, you know, it's diffraction limited, perfect mirror. You do have to worry about things like, you know, bugs landing in it and get stuck, and that causes scattered light, and you have to worry about ripples and wind blowing across it. There's lots of little complications that come with the liquid mirror telescope, but the main thrust of it was we could build a 3-meter telescope it was at about 2 orders of magnitude, a factor of 100 cheaper than building the same thing with glass and, you know, an aluminized mirror. So you can't steer it because it's liquid, so it has to look up. So it only looks at the zenith, and so you clock your CCD at exactly the sidereal rate. And so if you had an 8-hour night, you get a nice 8-hour image that was maybe only 2 minutes deep in terms of exposure, but you iterate night after night after night, or you change the filter and you build up a low resolution spectrum. And it worked. We got some data. We published a couple of papers. I was hospitalized a couple of times because I did ridiculous things. I'm not a very hands-on sort of person. I cut off a tip of my finger with a table saw, split my head open. I've got a whole talk on it. If you go to my YouTube channel, I've got a couple. There's a liquid mirror talk about exactly that, or just get me back to talk about it, because it's a fun, wacky story. All of the, you know, liquid mercury, it's dangerous.
Yeah, absolutely. I thought you were going to say you picked up a cup of mercury thinking it was a coffee or something.
There's all kinds of crazy, this was at a time, we built this out in my supervisor's back garden in Vancouver. This was at a time where the university was not paying attention to, health and safety or risk assessments. I was oblivious to this. I just did whatever I was told. I should have realized there was something suspicious when, liquid mercury, you can buy it, but it's expensive. But you can go to various industries who want to get rid of slightly dirty liquid mercury, but it costs a lot to get rid of it. And so we just took it off their hands for free. So I was sent literally at 3 a.m. to the dodgiest industrial estate outside of Vancouver. I didn't even question it. I just showed up at 3 a.m. These guys came out with a couple of big pallets filled with like 30 of these little pint-sized things of liquid mercury and loaded it into the back of the truck. And I left. Obviously, it was wildly illegal. It violated every sort of health and safety thing. But we got all this liquid mercury for free because it was slightly dirty, but it was fine for what we were. Not slightly dirty, just a little bit.
But you weren't using it in any chemical process.
So they didn't want to clean it. They didn't want to get rid of it the way they were supposed to. And again, I was a kid. I didn't know anything. I just did what I was told. I didn't know anything about health and safety or risk assessments and sort of stuff. So I've got a whole fun talk about some of the weird and wonderful things that eventuated from working on that project. That's why I jumped ship from planets to liquid mirror telescope, because it sounded exotic and fun and weird. And that's what I was looking for my PhD. Again, may not have been the best decision, but I can't really complain, but I missed out on any potential Nobel Prize on the planet discovery side of things, but there you go.
Fantastic. Okay, wonderful, Brad. Right, once again, everybody, to conclude, can we give him a really big traditional Hereford round of applause? Thank you.
Thank you so much. It was great, and we'll try. We'll
have to get you down here sometime, but we'll have you back certainly one way or the other. Okay.
Absolutely. Thank you, everyone. Thank you, Chris.
Thank you. We'll let you go home. All the best. So we'll call it a wrap. Bye-bye. See you.
Thanks, folks.
Bye.